time where we wrap up with this rotational vector field, I just want to comment about, I believe I say this is also known as radial vector field. That's not correct, all right? I think just in case you go back and you go back to the notes, or if you're watching these videos on the YouTube channel, just a note. I just know that I made a I called it in a way that it's not supposed to. Okay, let's have a look at another example. Okay. So for example number 3, let's sketch some vectors in the vector field given by 3xi plus 3yi. All right, how is that going to look like? Well, in a similar way we did yesterday, I'm just going to do a bunch of random vectors. I mean, a bunch of random points that will, of course, give us a bunch of random vectors. Okay, I'm going to go about the point 1, 0. Okay, 1, 0, 1, 1, 0, 1, negative 1, 1, negative 1, 0, and negative 1, negative 1. Just to come up with some random vectors. Okay, so in this case, I believe it's going to be a lot easier to compute the vectors related to each of the order pairs, to each of the points. So, because in this case, the x component of the vector, it's related to the x coordinate of the order pair, while the y component of the vector is the y coordinate. So it's not going to be reversed like in the previous example. So, okay, 1 times 3, that equals to 3. 3 times 0 equals 0. 1 times 3 equals to 3. 3 times 3 equals to 3. 0 times 3, that's a 0. 0 times 1, that's 3. Negative 1, careful, times 3, that's negative 3. 1 times 3 equals to 3. Negative 1 times 0, negative 1 times 1, negative 1 times 3 is negative 3, and 0 times 3, that's 0. Negative 1 times 3, that's negative 3, negative 1 times 3, another negative 3. So let's sketch these vectors using those order pairs, those points as points of reference. Again, when we plot vector fields by hand, we go to these ordered pairs, okay? And that's going to be our starting point for the vectors that we have on the second column. So for instance, I'm going to go to the point 1, 0. And from here, I'm going to plot the vector 3, 0. That is, from here, 3 units in the x direction, but no units in the y direction. So that's just going to be this vector here. At the point 1, 1, let's go to the point 1, 1. What vector do we have? So we have the vector 3, 3. That is 3 units, 3 units. Okay. At the point 0, 1, that is this point right here, we have the vector 0, 3. That is 0 units in the x direction, 3 units up in the y direction. All right. The next vector, okay, what's that? Negative 1, 1. That is negative 3. Negative 3, positive 3. Okay. Okay, what's the next point? Negative 1, 0, and negative 1, 1. So negative 1, 0, that's a vector, negative 3, 0. And lastly, at the point negative 1, we have the vector negative 3, negative 3. All right? So this looks like a bunch of vectors like out of the origin, like an explosion, if you will. So, well, actually, the purpose of these two particular vector fields is to later illustrate two of the most important operations in vector calculus or in vector analysis. Number 1, it's the divergence, and number 2 is it's the curl. The curl, it's a measure it's a quantity that measures rotation on a vector field. That's the previous example. That's how we can relate it. And the divergence, it's a quantity that measures expansion or compression, which is related to this vector. We're going to get into those two properties later. For now, we're just getting familiar with how these vector fields look like, how do we plot them. But of course, I mean, we don't have time to plot infinitely many of these vector fields. So to get a better picture of this, let's go about GeoGebra, right? Okay. Okay, so in GeoGebra, let me plot this vector field. So what do we have? Wasn't that 3x and 3y's? And 3y? so that's a 3x and that's 3y. All right. Do you see all these vectors like going out of the origin like an expansion? I mean, you could even change the sign of this this vector of these components, you know, just so you can see the difference. Let me change this to a minus, and let me change this to a -2. So what do we have in this case? We have the contraction otherwise, right? We have the vectors the other way. All right. So let's see. Let's go back to the notes and keep working with more vector fields. I mean, that's also known as the radial vector field, not the rotational vector field. So there's more examples. I mean that we can create using. Well, these are result of graphing this in GeoGebra. I just put the screenshots here. But I mean, the more complex or the more elaborate the functions, it gets a little bit harder to plot these vector fields. So in some cases, if I ask you to plot a vector field on a quiz or on an exam, I will give you something nice and easy like the ones we just did. These fancier ones, at least just know how they look like, at least know how to plot. If you want to play with other functions, you're free to do it. Just go Google GeoGebra vector field plotter or something in 2D, in 3D as well. We're going to look at the 3D ones. Yep, in a second, in a few minutes maybe. And you can play with your functions here. For instance, x minus 2, x plus 1. Let's reproduce this one. X minus 2. And what was that? X plus 1. X plus 1. Notice there's no y's. That's possible, right? That's how this one looks like, right? Does that looks like the one we have on the notes? Sort of, right? It's just the window what makes it look different. Maybe the extent of the vectors. Yes, much better. More vectors. The spacing in between. Oh yeah, that looks a lot more like the screenshot right on the notes. And I mean, you can fun and play with this however you want. Put your favorite functions. Put trigonometric. Put exponentials, logarithmic. That doesn't matter, right? Doesn't matter. All right. Let's see. What else do we have? Okay. So, oh yes, even vector fields in space. Okay. For this, I have another. I have another GeoGebra project for vectors in space. Okay, let me open it here. All right, and yeah, let me change the functions here. Okay, what's the function on the nodes? Oh, simply x, y, z. Okay, does that look familiar? Somehow looks like the radial vector field in space. How do we know it's the radial vector field? Because look at the x component and the y component of the vector field. It looks like x and y. In our lecture example, it had a 3 in the coefficient. So, and naturally for the k component, we would use the other letter in the alphabet, the z variable, right? So let's plot this vector field right here. So that's x. Should I do tab? No, it doesn't work with a tab. X, y, and z. All right. And okay, let's see if I can. And this is how the vectors look like. All the vectors pointing out of the origin. Looks a lot like what we have on the picture. So for the extent, can I make this look longer? Maybe with a 5 right here. Yes. The scale, oh, it's the scale, that's 2. Let me make it a 2. Let me make this a 1 again. So, oh yes, it looks looks better, right? Looks easier to visualize what's going on. It's like an explosion or like an expansion, because we could change the signs, I think. Let me change the signs of this. Let me make this negative. Negative. Hopefully this works. And no, it's not working. I was hoping this would go in the opposite direction, but anyway, So that's how these vector fields look like. Well, let's talk about other properties of these vector fields. Well, actually, let's talk about a vector field that you guys are familiar with, but you didn't know it was a vector field because back then we were not ready to call, hey, this is a vector field, because, well, that was more like an operation to which is finding the gradient. And again, the gradient gives us a pretty good information that's a vector. Those components of the vector, that's the direction in which we need to go in order to go in the direction of, what's that, the steepest ascent, right? And in the opposite direction, that takes us in the lowest ascent or steepest descent, right? So so for instance, the gradient, which you know how to find, you're given a function. It's a scalar function, either in R2 or in R3. That's going to be a vector field. So let's find the vector field for the potential function f. Well, what is a potential function? Well, so the potential function, it's a function whose gradient is what we're going to get. That's because we're going to go back. So later when we get to conservative vector fields, we're going to go back to obtaining the original function. Given a vector field, we will determine whether this function, or whether this vector field is conservative. Well, that's one of the most important tools for vector calculus, you'll see. Okay, find nabla of f. Find the gradient of f. Okay, partial derivative of x squared y with respect x, that's 2xy. Do we have x's here? That's 1 times 4z cubed. So that's our derivative with respect x. With respect y, okay, that's 1 times x squared and 1 times negative 8z. And lastly, with respect z, that's 0. That's 3 times 4, that's 12. Xz cubed, right? I mean xz squared. And the derivative with respect x, that's a with respect y, that's a negative. Oh wait, with respect z, negative 8y. So that's the gradient. All right. So that is the gradient, which is a vector field. You know, it has components x, y, and z. It has 3 components. A vector function, but it's no longer depending on t. This is not describing the position of a particle on a trajectory at different values of time, at different values of t, because this is not a function of t. This is a function of x, y, and z. So here we're getting different vectors at different points in space, and those vectors again work like streamlines, which again can help a particle traveling along a particle move faster or actually move slower. That's what we're going to do later when we look at what you call line integrals. Okay. One more definition and we're good to go to the next section. Let's see. Equipotential curves are equipotential curves that are the level curves of a potential function. So the gradient field is everywhere orthogonal to equipotential curves. What are those equipotential curves? Well, we have worked with this before with a different name. Those are just the level curves. All right, it's just a different name. Okay, so let's consider this function. F of x y equals to x plus y squared. They're asking us to sketch several curves for this function using c equals 0, c equals to 2, and c equals to 4. Okay, so let's, again, to sketch level curves, we set this guy equal to c, and we just give the different values of c that we're requested to do. So number one, for c equals to 0, what do we get? Okay, so that's x plus y squared equals to 0. And in this case, that's x equals to negative y squared. So we're going to have a sideways parabola also pointing towards the left because of the negative sign in here, all right? For c equals to 2, that means x plus y squared equals to 2. X equals negative y squared plus 2. And lastly, for c equals to 4, that is, what's that? X plus y squared equals to 4. That is, x equals to negative y squared plus 4. So in this case, again, we're graphing sideways parabola. So the first one, it's easy to plot. All right, so the first one, that is 0, 0, 1, negative 1. So that's 2, negative 4, 2, negative 2, negative 4. So that is our first level curve. All right. Okay. So the second curve, it's going to be the same sideways parabola. But what is that plus 2 going to do on that sideways parabola, by the way? Looks like up, right? However, that's if we had functions of x, but this is a function of y. Okay, so it's pointing to the left, but the 2 shifts it to the right, right? That's correct. Okay, so and 4. Yeah, and that's 4. Okay. Anyway, like this, and 4 units, right? Okay, so these are the level curves. Now let's verify this definition here on part B and on the next page. Find the associated gradient field and sketch several representative vectors on your graph above. All right. So find the gradient, that is, okay, our function f of x, y, that equals x plus y squared, okay? So let's find nabla of f, that is the gradient of f, that's the partial derivative with respect x, that is 1, and the y component of this vector field is the derivative with respect y, so that is 2y. Okay, so we need to sketch some vectors. And well, in this case, I'm not just going to do random points. Well, I'm going to give you some points that are on the graphs of these sideways parabolas we just plotted by hand. So, number 1, that's the point 4, 0, 3, 1, and 0, 2. So let's get the associated vectors. Well, notice in this case, this vector field has a constant x component. It's 1 for all. It's 1 for all of them. All right? It's 1. And then for the y components, we need to multiply the y coordinate by 2. So that is 0 times 2, that's still 0. 1 times 2, that equals to 2. And 2 times 2 equals to 4. Okay? Let's plot these vectors in these corresponding points. So let's go to the point 4, 0. Okay, so the point 4, 0. What vector did we get there? Didn't we get the vector 1, 0? So from here, I'm going to go 1 unit to the right and 0 units up. Let's go to the point, what was that? 3, 1, right? So from here, from the point 3, 1, I'm going to go about the vector that is 1 unit into the right, 2 units up. And lastly, at the point, what was that? 0, 2. Okay, so maybe I should, 0, 2, that's here. That's the vector. What vector did we get? 1, 4, right? That is 1 and then 1, 2, 3, 4. There you go. Look at this picture. Look at this picture. Does the gradient field look orthogonal to the level curves, to the equipotential curves? So these vectors I'm plotting form a vector field, a streamline, right? And that looks a lot like similar to the radial field, right? Like that describes some kind of expansion. Well, not compression because it's going outside of the origin, of course. And yes, this verifies this definition that all these vectors see how they form a 90-degree angle. I mean, it's kind of weird to talk about a 90-degree angle because it's a curve, right? So unless it was like a diagonal line, so that's easier to see that 90-degree angle. However, if you zoom in, like really zoom into, like, say, x equals to 0.00001, so the more you zoom in, the more like a straight line is going to look like. So that's what makes the 90-degree angle to show for us. All right.